All right, welcome everybody. In this video, we'll explore how to construct a confidence interval for a difference in two proportions from two independent populations. And so we've worked with confidence intervals for a difference in two proportions using bootstrap distributions. So now we're going to develop a method, a parametric method for constructing these confidence intervals using the central limit theorem. And so before we jump into looking at the difference in two proportions, it's going to be very similar to how we've constructed parametric confidence intervals for other statistics. So I want to make sure that we connect what we're doing with confidence interval for a difference in two proportions with the intervals that we've already worked with. And so how that process works when we've constructed confidence intervals for some population parameter theta, and this might be a mean, a population mean mu, or a difference in two means mu1 minus mu2, or it could be a proportion p, a single proportion. What we'll work with today is a difference in two proportions, p1 minus p2. But whatever the population parameter that we want to estimate is, we start by picking a random sample, and from that sample, we can compute a sample statistic that would be reasonable to use as a point estimate for that parameter. Then we calculate margin of error since we want to account for the variability in the sample statistics. We construct the margin of error based on the standard error of a sampling distribution for the estimator theta hat. And then we construct an interval estimate by taking our point estimate and adding and subtracting the margin of error to get an interval of plausible values for the population parameter theta. So what I want to discuss now is how we can apply this same process for constructing a confidence interval for the difference in two proportions p1 minus p2. And so let's first recall the central limit theorem for a single proportion, since what we ultimately want to find is the standard error for the sampling distribution for a difference in two proportions. And this is going to use some facts about a sampling distribution for a single proportion. So if X is a binomial distribution where we're having n trials, each with success P, then the sampling distribution for the proportion P hat, which is going to be the number of successes X, divided by the number of trials N, that this distribution, the expected value is going to equal the population proportion, and the variance of this sampling distribution is equal to P times 1 minus P all over N. And so this comes from facts that we discussed about binomial distributions. And so for sampling distribution for a difference in two sample proportions, P hat 1 minus P hat 2, well, now we have two independent binomial random variables, X and Y. So X has N1 attempts, each with success, probability of success P1, and Y has N2 trials, each with success P2. And the difference in sample proportions, therefore, is going to be X over N1 minus Y over N2, and that we denote with P hat 1 minus P hat 2. And so for the expected value of this difference in sample proportions, we can use properties of expected value, which basically says we can break up addition and subtraction and pull out constants. So this expected value of P hat 1 minus P hat 2 is equal to the expected value of P hat 1 minus the expected value of P hat 2. And from the central limit theorem for a single proportion, we know that each of those expected values is going to equal their respective population proportion. So the expected value for the difference in the sample proportions is the difference in the population proportions, P1 minus P2. And when we're constructing a confidence interval for the difference in two proportions, in order to find the margin of error for our interval estimate, what we really want to track down is how much variability is there in the sample statistics. In other words, what is the standard error for the underlying sampling distribution for the difference in sample proportions? So let's take a look at the corresponding variance that we would get for the distribution, the sampling distribution of the difference in sample proportions. So similarly using properties of variance, if I want to calculate the variance of the difference in these two sample proportions, I could use the fact that we can break up addition and subtraction, but we need to be careful that when we break up these linear combinations, when we pull out the constants, such as the negative times p hat 2, when we pull that constant out, we square it when we pull it outside of a variance. So that becomes a -1 squared, and therefore the variance in the difference in the sample proportions is equal to the sum of the variance of p hat 1 plus the variance of p hat 2. And so these formulas, p1 times 1 minus p1 all over n1, that comes from the central limit theorem for a single proportion. So we take the variance for the distribution of sample proportions p hat 1, and we add to that the variance for the distribution of p hat 2. And therefore, the standard error for the distribution in the difference in sample proportions is going to be the square root of that variance. So we take the square root of the formula that we have up above. And so now that we've got a standard error, or an estimate for the standard error for the sampling distribution of the difference in sample proportions, we can now use that to construct a confidence interval for the difference in proportions. So we can modify the Wald confidence interval that we used for a single proportion and just use this same blueprint that we've been using to construct parametric confidence intervals. So the first thing we do is we pick a sample statistic as a point estimate. And since we want to estimate P1 minus P2, we're going to take the corresponding difference in sample proportions, P hat 1 minus P hat 2. So that's going to be our point estimate. Then we can calculate the standard error using the central limit theorem. But we have an issue here in that the central limit theorem requires us to know what P1 and P2 are in order to calculate the standard error. And those are unknown. That's the whole point here. So what we can do is use our sample proportion from population 1, P hat 1, in place of P1. And we use the sample proportion from the other population sample, P hat 2, as a replacement for the value of P2. And then we can calculate the standard error using the sample proportions instead of the unknown population proportions. And then finally, we're going to calculate the margin of error depending on the confidence level that we want to use for the confidence interval. And in the case of a difference in proportions, the underlying distribution that we're going to use is going to be the standard normal distribution, because we're modeling a binomial distribution with a continuous distribution. So it makes sense to use a normal distribution as our estimate for the binomial distribution. So we get, therefore, a confidence interval estimate for P1 minus P2, which is going to be approximately the difference in the sample proportions plus or minus some margin of error that we get by using the standard normal distribution and using this estimate for the standard error. And so luckily, if we're working in R as we are here in this Colab document, there is a built-in R command called prop.test that works similar to the t-test function that we've seen, that we can use to generate a confidence interval estimate for a difference in two proportions. And so the command, again, is prop.test. And in this case, we have a pair of successes and a pair of total sample sizes. So x1 is denoting the number of successes from sample 1, which has size n1, and x2 is denoting the number of successes in sample 2, which has sample size n2. And then we input the confidence level as a proportion, and then with working with proportions, we can decide whether or not we want to apply a continuity correction. So if we don't want to apply this continuity correction, we use the option false. And if we do, we use the option true. And we've seen how these continuity corrections work in the past when we were using a normal distribution to approximate a binomial distribution. So it works the same here. And the one thing I want to clarify is that when we used prop test for constructing a confidence interval for a single proportion, the output by default is a score confidence interval. When we're using prop test to construct a confidence interval for a difference in two proportions, the default is we're going to get output, which gives us a Wald confidence interval. And there are other types of confidence intervals that we can use for a difference in proportions. For example, with a single proportion, we looked at Wald, Agresti-Cole, score confidence intervals. There are other types of confidence intervals for a difference in proportions, but we'll just stick with the Wald confidence interval, which is the most commonly used confidence interval for a difference in two proportions. Okay, so let's see how we can construct a confidence interval for a difference in two proportions. And the example that we'll use is data from a recent, well, at least from 2021, depending on when you're watching this video, poll by PBS, NPR, Marist, which asked people, among other things, what their political party affiliation was and whether they were planning or had already gotten vaccinated for COVID-19. So this was around the time that the COVID-19 vaccines were becoming available for the public in the United States. And so from this table, what we will approximate is going to be, we'll construct a confidence interval to estimate what proportion, what is the difference in the proportion of Democrats that said they did not plan on getting the vaccine compared to the proportion of Republicans that said they were not planning to get the vaccine. And so if we want to do this really quickly in R, we can use the prop.test function, which is down below, to construct this 90% confidence interval. And so first we observe that the total number of successes, in this case, a success is we're considering someone that does not want to get vaccinated. That's what we're counting. So there were 40 people from the first sample of Democrats that said they did not plan on getting vaccinated. And there were 120 out of the sample of Republicans. So we put a 40 and a 120 inside this entry. Then we enter two corresponding sample sizes. And here we, of course, want to be careful about the order. So since I first entered the number of Democrats that didn't want to get vaccinated, the first entry here is going to be the total sample size for the Democrats, followed by the size of sample 2, which in this case is the total number of Republicans that were in this sample. And so if I don't want to apply a continuity correction, I could use the option false over here. My confidence level is 90, so I use 0.9 for the confidence level option. And here I'm just going to parse out the output that for the corresponding 90% confidence interval. So running the code here, we can see without a continuity correction, we get a confidence interval that is going from minus 0.3566 up to minus 0.2479. So in other words, we can see that the plausible range of values for the difference in these two proportions, it falls somewhere between these two cutoffs. If we want to apply a continuity correction, I enter the same command, but I just change the correct option from false to true. And you can see here we get a slightly different confidence interval. The cutoffs are a little bit different, but they're really close to each other. And in both of these cases, what's important to note here, if we want to kind of interpret what's significant about this confidence interval, that we can see that the range of plausible values for the proportion of all Democrats that do not plan on getting vaccinated minus the proportion of all Republicans that do not plan on getting vaccinated, we're only getting negative values. So the only plausible estimates that we're getting are negative. So that would imply that the proportion of Democrats that don't plan on getting vaccinated is less than the proportion of all Republicans that do not plan on getting vaccinated. Okay, and so the prop test command in R is very nice. We get these confidence intervals as the output, but it's kind of like a black box. We're not quite sure what's going on underneath the hood. So let's verify these results using the formulas that we derived earlier in this video. So let's first take a look at how this calculation would work without a continuity correction, without applying a continuity correction. So the first step in constructing these confidence interval estimates is we first find a point estimate for the population parameter that we're trying to estimate. So in this case, we're trying to estimate the difference in population proportions, PD minus PR. So a reasonable point estimate would be the corresponding difference in sample proportions P hat D minus P hat R. And so this R code cell here has the values for X from the table up above for X1 and N1. So this is the Democrat sample. This is the Republican sample. And then we take the difference in those two sample proportions. And we can see that a reasonable point estimate for the difference in the population proportions would be minus 0.3023. Next, we go ahead and estimate the standard error, and then we use the standard error to calculate the margin of error. So the formula for the standard error that we're going to use to estimate the standard error, we derived earlier in this video. And so we just plug in the sample proportions that we've already calculated for Democrats and Republicans, and we plug in the corresponding sample sizes for each of these samples. And in the code cell below, we get the standard error. So we can see here the corresponding standard error is 0.0330. And for the margin of error, we're using a 90% confidence level. So we could use the QNorm function, which is in the R code cell below, for a 90% confidence level. Keep in mind, the middle area is 90%, and then the area in each tail is 5%. So that's why we enter 0.95 to find the Z alpha over 2 value, and that works out to approximately 1.645. So the margin of error is going to be that Z alpha over 2 value times the standard error that we calculated above. And so we get a margin of error for this 90% confidence interval, which is 0.0544. And so now that we've got our point estimate and we've got our margin of error, then we're able to go ahead. I forgot to run this code cell over here. Then we're able to go ahead and calculate a 90% confidence interval for the difference in the proportion of Democrats and Republicans that do not plan on getting vaccinated. And so for the lower estimate, we take the point estimate and we subtract the margin of error, and that gives us a lower cutoff of approximately minus 0.3567. And for the upper cutoff, we take the point estimate and add the margin of error, and that gives us an approximation of, or an upper cutoff of approximately minus 0.2479. And so those are the outputs that we get using the formulas that we derived above. And just to check this again with the output that we get from prop test, we can see here that we're getting exactly the same results as R, which is great. Applying the continuity correction is a little bit trickier. So I'll just leave this information down below if you're curious about how to verify the output that we got when we did apply the continuity correction, which was a slightly different confidence interval. You can read through the information above if you're curious how you would apply a continuity correction if you were doing this yourself. And there's some additional information down here about just summarizing all of the different confidence intervals that we've looked at so far, and the corresponding conditions that we would want to check before we go ahead and apply these parametric methods. So if we want to use the central limit theorem, then we need to make sure that our sample is large enough, and that means different things in different contexts. So you can refer to the end of this document for a nice summary. Okay, thanks everybody.